Welcome to the next chapter on force. Now, when a car is still on the road, we call on good Samaritans to help push the car. If you apply brakes on your bike, it slows down and finally comes to a stop. If a car is speeding on a highway and you suddenly applied brakes, not only does the car slow down, it may also waver on the road, which could be dangerous. This rock resting on a table, if you have no use for it, you might push it away, and when you need it, just pull it back. In all these cases, what we are seeing is a change of state. Something at rest starts to move, or something in motion coming to a stop. What produces this change of state is something called a force applied on the said object. A force is a push or a pull. It acts in a particular direction and the impact depends on the size of that force. So then, a force has both magnitude and direction. Such quantities are called vector quantities. When a force acts on a body, it may 1. Make a stationary object start moving or increase the speed of a moving object. It could also slow down a moving object or ultimately bring it to a stop. A force could also produce a change in direction of a moving object. It could also distort or change the shape of an object. The SI unit of force is newtons. This chapter, we shall look at the types of forces and their effects on matter. And we start with gravitational force, or the force of gravity. Gravity was first explained by Sir Isaac Newton. Seated under a tree and a fruit fell on him. And so what Newton wondered to himself is, why wouldn't the fruit have gone the other way, upwards, not downwards? It is common knowledge today that when objects are thrown up from near the Earth's surface, they always fall downwards towards the ground. Newton discovered that the Earth exerts a force of attraction on any body or object near its surface, and this is gravitational force, or the force of gravity. But more specifically, gravitational force is the force of attraction between two bodies of given masses. Objects with large masses have higher gravitational force or pull. The gravitational force between two objects also depends on how far apart they are. The closer they are, the stronger the gravitational force between them. You and the Earth have masses, so you pull on the Earth and the Earth pulls on you. But the Earth's mass is much larger than yours, so its gravitational pull is enough to keep you on its surface. When you jump, you pull from the Earth, but because of the larger gravitational force of the Earth, it pulls you back down. Each planet exerts its own gravitational pull on the Earth. Astronauts on the Moon experience about 1/6 the gravity on Earth, and this is because the Moon has a smaller mass than the Earth. This is why people weigh less on the Moon, because weight depends on the gravitational force on an object. The force of gravity have kept the Earth and the Moon in their orbits for 4.5 billion years that they supposedly have been in existence. So the Earth and the Moon are in a kind of tug of war, pulling on each other. This kind of pull is evident in the rising and falling of tides in the oceans. Let's see something about free-falling objects. So the force of gravity of the Earth pulls all objects towards it. Suppose you drop simultaneously a stone and a small cotton ball from a height. Which reaches down first? The stone, you would say. And you're right. Do you think heavier objects fall faster than lighter ones? That is, they accelerate faster than lighter ones. It would surprise you that indeed that is not the case. Galileo Galilei showed that all objects, irrespective of their masses, fall at the same speed towards the Earth. He explained that the only reason why lighter bodies fall slowly is due to air resistance, and this was proved later by Robert Boyle. He placed a feather and a coin in a bottle and removed all the air in the bottle, creating a vacuum. When the glass was inverted, the coin and the feather reached down at the same time. Thus, acceleration produced in all free-falling bodies is the same and is independent of the mass of the falling object. The next force is tension. The pull or compression of a spring or a string at both of its ends is called its tension. If you push a spring, it pushes you back. If you pull it, then it pulls you back again. In fact, a spring exerts a force on the object that is attached to it in order to restore its shape. When no force is attached to the spring, the length of the spring during its relaxed state is called its natural length. The restoring force of a spring is directly proportional to the deformation length. Here, the guy pulled the spring by a distance x and the natural length of the spring is L0. Because the spring is elongated by a length x, an inward restoring force will act. This force will be proportional to the elongated length. Thus, restoring force is equal to Kx, where x is the constant of proportionality called the spring constant. If the boy pushes the spring inwards, then the spring is compressed and again will apply a restoring force in outward direction. If the compression length is x, the restoring force is equal to Kx. Therefore, restoring force will always be equal to Kx. Now, for various values of force and corresponding distance x and plotted on a Cartesian plane, it produces a linear or a straight graph through the origin. This is called Hooke's law. So some forces compress bodies and are called compression forces. A compressed or stretched object will tend to regain its original shape when the stretching or compressing force is removed. Materials that can be compressed or extended without breaking are called elastic. Spring balance, an instrument used to measure force. The next force is buoyant force or upthrust force. Now, if you push a coin in a water trough downwards, release it, it bounces back to the top surface. To keep it beneath the water surface, you have to exert a downward force. This means the cork is experiencing an upward force. The upward force is exerted by water and we counter this force by applying a downward force. This shows that when a body is partially or wholly immersed in a fluid, the fluid exerts an upward force on the body. This upward force experienced by a body when partially or wholly immersed in a fluid is called upthrust or buoyant force. The phenomenon responsible for this upthrust is called buoyancy. Let's see an experiment. We suspend a body from the hook of a spring balance and observe the readings. We then immerse it in a trough containing water. We observe that the reading on the spring balance is indicating a lesser weight of the object. Again, if we remove it from the trough, we observe that the reading is back to the original figure. This shows that any object partially or wholly immersed in water or any fluid experiences an upward force called buoyant force, and this force is responsible for the apparent loss in weight of the object immersed in it. The difference in the two readings is the upthrust force. Cohesive and adhesive forces. The force which keeps molecules together is called the molecular force. The force of attraction between two similar molecules is called cohesive force. The force of attraction between two different molecules is called adhesive force. When a narrow tube is dipped into a fluid, the fluid rises in the tube. This is called capillary action. Capillary action is the result of both cohesive and adhesive forces. Cohesive forces exist amongst the fluid molecules, while adhesive forces exist between the fluid molecules and the walls of the glass tube. In this drop of ink, the molecules are held together by cohesive forces between the molecules. When the drop hits the surface, it spreads out due to adhesive forces between the fluid molecules and the paper surface. The meniscus in a fluid held in a tube is due to either cohesive or adhesive forces. If the cohesive forces are stronger than the adhesive forces, then a convex meniscus is formed. If the adhesive forces are stronger, then a concave meniscus is formed instead. Next is frictional force. Suppose you give a push on this block resting on the table. You observe that it stops after a while. If you push it from the other side, the same thing happens. It stops. When we push the block, we apply the force. But the impact of that force don't seem to last. Obviously, there must be another force acting to counter the force we applied. This is called the force of friction. If you apply the force along the left, friction acts along the right. If you apply the force along the right, friction acts along the left. But in both cases, friction opposes the motion of the block. Friction is the force that opposes motion. In this case, friction acts between the surface of the wooden block and the surface of the table. What factors affect friction? We make an inclined plane on a smooth table, say using a wooden board supported by books. Put a mark with a pen at any point on the inclined plane. Now let a pencil roll down the plane. Note down the distance. Now spread a piece of cloth over the table and make sure there are no wrinkles on the cloth. Roll the pencil once again and note down the distance. The distance covered in this case is less than for a smooth table. Friction is caused by the irregularities on the two surfaces in contact. Even surfaces appearing smooth have minute irregularities on them. Friction is caused by the interlocking of the irregularities on the two surfaces. Obviously, friction will increase if the two surfaces are pressed harder. Try and move a box at rest. you find that usually it is tough to get it started. The force required to overcome friction at the instant an object starts to move is a measure of static friction. Again, push a car that is already in motion. The force required to keep an object moving with the same speed is a measure of sliding friction. When the car starts sliding, the contact points on its surface do not get enough time to interlock with the contact points on the road surface. So the sliding friction is less than the static friction, and this is why it is easier to keep a car in motion than to get it started. If there was no friction, an object in motion would remain in motion forever, but friction often brings moving objects to a stop or even cause a change in direction. Friction causes wearing out of moving parts like car tires and machine parts. It can be reduced by oiling or using ball bearings. Next is surface tension. Have you ever seen a needle floating on water or an insect walking on the surface of water? How comes a needle, though being denser than water, floats, and an insect able to walk on the water surface? It is because the free surface of water, which is at rest, behaves like a stretched elastic membrane supporting the needle and the insect. This property of liquid is called surface tension. Surface tension is a property of matter by virtue of which the free surface of the liquid at rest behaves like a stretched elastic membrane having contractile tendency. Let's look at the surface tension in terms of molecular forces of attraction. Consider three molecules A, B, and C of a liquid. The dotted circle drawn around each molecule represents the sphere of action of each molecule. Observe that the sphere of influence of the molecule A is completely inside the liquid. It is attracted equally in all directions by the other molecules. There is no resultant force acting on the molecule A. The molecule B, closer to A, also does not experience any resultant force. How about C? A part of the sphere of action is above the liquid surface. The molecule C experiences a resultant downward force. Now consider molecule D that lies on the liquid surface. This molecule has its sphere of action exactly half outside and half inside the liquid. Therefore, the molecule D experiences a downward attractive force. Due to this downward force, the molecules on the surface experience a tension called surface tension. If you take a camel brush, dip it in water, its bristles get separated from each other. When you pull it out, the bristles cling together as the free surface of water film tries to contract due to surface tension. When a circular wireframe is dipped in a soap solution, it forms a thin soap film. Let's place a cotton thread on the soap film. The cotton takes on an irregular shape. When you prick the film gently with a hot, sharp needle, the film in the loop disappears and the loop of the thread takes a circular shape. By adding oil in water, we reduce surface tension. Therefore, the mosquito eggs and larvae cannot float but will sink and die, thus controlling their breeding. Surface tension is therefore affected by impurities and also temperature. Impurities reduce the surface tension of a liquid, Detergents, for instance, weaken the cohesive forces between liquid molecules. When temperature rises, the kinetic energy of the molecules of a liquid is increased. The intermolecular distances increase and the force of cohesive is decreased. Therefore, the surface tension is lower. The next force is the magnetic force. The force which causes attraction or repulsion by magnet is called a magnetic force. A magnet has two types of poles, a north pole and a south pole. Like poles repel, while unlike poles attract. Some materials are attracted by a magnet while others are not. Those which are attracted are called magnetic materials, while those that are not attracted are called non-magnetic materials. Centripetal force is a force which constrains a body to move in a circular path or orbit. This force is directed towards the center of the orbit. Examples where centripetal forces are applied include a stone tied on a string or a sling, separation of ghee from milk, and the merry-go-round. The next force is action and reaction. Now, when a rock is placed on a table, its weight, that is action, acts on the table. It is pressed on the surface downwards. The reaction, that is opposite force of the table, acts on the block. In this case, there are two forces acting in opposite directions. One of the forces is called action and the other is reaction. Action and reaction are equal and opposite. That is, when one force acts on a body, an equal and opposite force acts on another body. So now, over with the forces, let's look at mass and weight. While mass is the quantity of matter present in an object, weight is the measure of the pull of gravity on the same object. This pull of gravity is always directed towards the center of the earth. Therefore, weight has both magnitude and direction. The SI unit of weight is Newton. Weight is measured by a spring balance calibrated in newtons. Due to the shape and rotation of the Earth, the weight of an object varies from place to place. The Earth is not a perfect sphere. It is flattened at the poles such that the distance between the center of the Earth and the poles is shorter than between the same center of the Earth and the equator. Therefore, a body weighs more at the poles than at the equator. On the Earth's surface, an object of mass m has a gravitational pull of mg on it, where g is acceleration due to gravity or free fall. Therefore, weight w is equal to mg, that is mass times the acceleration due to gravity. The Earth pulls each kilogram of mass on its surface with a force of about 9.8 newtons, which is approximately 10 newtons per kilogram. Compare this with the value of W over m from the experiment. For example, the weight of an object whose mass is 25 kilograms is given by weight is mg, so 25 times 10 gives us 250 newtons. Equally, the mass m of an object whose weight is 450 newtons is given by mass is equal to weight divided by acceleration due to gravity, which gives us 450 over 10, and that is equivalent to 45 kilograms. How do we measure force? A spring balance extends when a stretching force is applied. The larger the force, the more the spring extends. The extension of a spring can therefore be used to measure an applied force. Such an instrument that uses the extension of a spring to measure force is called a spring balance. A spring balance measures forces and should therefore be calibrated in newtons. However, there are some spring balances that are calibrated in kilograms. In such cases, one is advised to convert the kilograms into newtons. A kilogram mass has a weight of about 10 newtons. Next is scalar and vector quantities. Now, a scalar is a quantity which has magnitude, that is size, but no direction. It can be specified by a number and a unit. If the mass of a car is 800 kilograms or the area of a circle is 314 centimeters squared, then the values represent the magnitude of mass and area respectively. The mass and area are scalar quantities. Other examples of scalar quantities are density, volume, energy, time, pressure, temperature, and length. Scalar quantities are added by normal rules of arithmetic. For example, 2 kilograms added to 4 kilograms makes 6 kilograms. 4 hours added to 6 hours would make 10 hours. On the other hand, a vector quantity is a quantity which has both magnitude and direction. It can be specified by a number, a unit, and direction. If the weight of a car is 8,000 newtons, for instance, 8,000 gives the number. N is its unit and is directed towards the center of the earth. Other examples of vector quantities are force, velocity, displacement, acceleration, momentum, and magnetic field strength. When you divide a vector quantity with a scalar quantity or multiply a scalar and a vector quantity, the resulting quantity is always vector. All vector quantities obey a special rule for addition and subtraction, which takes account of direction as well as magnitude. A vector quantity is represented on a diagram by a straight line with an arrow. The length of the line represents the magnitude of the vector quantity when drawn to scale, and the arrow shows the direction and line of action of the vector. The sum of two or more vectors is the resultant vector.
Now, you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cornelius at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.